Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Today I'll talk about one of my recent work on matrix factorization. Okay, I will try to make it intuitive, and Danny told me don't make it too mathematical, instead like a conference talk. So I try to give more motivation and try to explain why do we do this. Okay, so if you have any questions, just interrupt me. I will be happy to answer you. Okay, so matrix factorization. It's very simple, right? So we have a simple formula, x equals ZA. And in practice, Z is approximately equals Z and A. And X is observed. And Z and A are two latent matrices. So if A has a low dimension, for example, this is the dimensionality of these matrices. So n data points, each row is one data point, will have multiple features. Okay, I'll explain in concrete context in next slide. But now just remember we have this matrix factorization. One key issue is the dimensionality of Z and A. Okay, so how many columns you're going to have in Z? In other words, how many rows you're going to have in A? This is a classical model in statistics. For example, PCA, principal component analysis, or ICA, independent component analysis, or factor analysis. You can name lots of models following the same equation. By embedding the data, by making K to be a small number, we can review latent structures in the data. So that's actually the idea used in PCA, for example. You can summarize the data by a few eigenvectors. Okay, you can use it for computer vision or many other tasks. Okay, let's see. What's different in this work is a different power distribution, different constraints will be used on latent matrices Z and A, such that we have different properties in this infinite matrix factorization. Here is one observation X. We should rotate it, actually. Now look this way. Each column is the column index users. Okay, this is a rating matrix. Row are objects, items, say movies. This movie 1, movie 2, movie 3, movie 4, movie 5, or books. Okay, so now we want a recommendation system. Say Alice had watched movie 1, X-Men, or something else, Matrix. And the other person, Bob, watched Terminator, or didn't like Terminator apparently, or Forrest Gump. Now, based on similarities between the users, we try to predict how likely Alice will like the second and third movies. Okay? So this is common in many online recommendation systems. For example, like Amazon. If you ever use Amazon, they have stars, 5 stars representing you like a particular book. 1 star, maybe you are not really into this type of books. Okay? So we can translate it into a matrix. Zero, actually, zero means no interest at all whatsoever. Okay? So it's a non-negative matrix factorization. Okay. The prediction task is basically filling the missing elements. So as I said, the goal is filling the missing elements is essentially a prediction task. Predicting the user preference based on how the other users rate the movies or books. Okay? So one concrete example is this. If you like movies A, B, C, D, E, and I like a movie A, B, C, D, but I haven't seen E yet, so what will be my possible rating on E? So simply put, very likely I would like E as well, because based on the similarity between your preference and my preference, we share lots of common favorite movies. The algorithm might infer, oh, maybe I would like E as well. So I have a large value for this movie. Okay? So this can be addressed by collaborative filtering. In other words, in particular, this matrix factorization model. So we want to fill in missing elements of X. But to do that, we learn latent matrices Z and A. And once we know Z and A, we can use the value of ZA to make predictions on the missing elements of X. Okay? So let's try to interpret the meaning of individual elements of the matrices. Xij will be user I's preference, a rating on movie J. Okay? Zik is user I's interest in movie category K. For example, action, romance, comedy, thriller, you name it. AKJ will be how likely this particular movie belongs to category K. So then the user's preference will be how much I'm into romance or thriller or action multiplied by the movie's membership in different categories and sum together. That's the intuition, okay? So far, any question? Okay, super easy. Okay, let's make it a little bit faster then. Another application, text modeling. Oh, good.
What's the typical size? So is K typically much smaller than A and B?
K is smaller than D, no, than N. K is smaller than N normally.
Much smaller.
And actually, the beauty of this talk is this. We will have a distribution on all the possible matrices. Actually, the size will be infinite. And therefore, we will model uncertainty in the size in the other possible matrices. We will we'll choose basically a good K automatically from data. We'll learn K from data. Empirically, it's smaller than N. You can easily, actually, that's what we observed later on. We'll see the rating on different data, like Gessler data set. You're familiar with it. It's a small data set, has 73,000 users. So N is big, but K is only like 8 or 9. So K is a lot smaller than N. So essentially the idea is we have a high dimensional data set, a project into low dimensional space. We use that to summarize the original observation. Okay?
Yeah, I think K might be the number of factors which control how people read each movie or something.
Yeah, exactly. Essentially number of factors, number of bases. That's the classical interpretation for factor analysis, right? Okay. But I want to emphasize that in this work, we're using Bayesian approach. Really, we saw a distribution on the other matrices. We'll compute a posterior distribution. In other words, we're not getting a particular matrix. No, we'll not provide you a single solution. We'll give you a set of solutions, tell you how good for each solution in terms of probabilistic framework. Okay, so another application, text modeling. So we want to give you a text, a document, web page, a news group article. Can you review how many latent topics in the document? Okay, this is a bad example, but I use it. It's my student. Student took it from his homework. Asked him to give me a slide. So this is there's no pointer. Suppose we have 4 articles from computer science. C stands for computer science. 3 from biology. Okay, and these are words. And here's the simplified version, meaning if a word appears in a document, it will be 1, if otherwise 0. Actually, it could be any number, it's not 1, it could be counts or TF-IDF features. Okay, from this you can see different words appear in different articles. If a classical compiler book, maybe only CS word, only this article will have this word. If it's an article about, say, computational biology, maybe there are words appearing both in these articles and those articles. Now the issue is, can we identify the latent topics automatically from the data? And give you a good summary of these documents. Okay, collection of documents. Each document will corresponding to a row of the matrix in X. Okay, Once we have that, we can do matrix. Once we have observation, we can factorize this dark X into ZA. And each row A will corresponding to one topic. Z will corresponding to the loading matrix. Basically, how do we generate a document by combining different topics together? Okay? And once we have that, we can also do clustering. Basically, based on Z, that will be projection coefficients. And we use it to do clustering easily.
So I have one problem about the numbers 3 and 1. So the gene is also gene at the C3 and number 1.
Yeah.
Yeah, that means it's a part of computer science.
Yeah, so that, for example, this article would be a
For both.
computational biology paper.
Okay, so that's only one from here.
Yeah, but this is a simplified version. You quantize them into one already. It could be any real number. That's what we do actually. In our real simulation, we use the TF-IDF features.
For the upright correlated what zeros is no one.
Because all these words only used in pure CS articles, not in biological articles. Okay? Here's another application. So I just throw out many applications. Hopefully I can somehow convince you this is useful. That's the idea. This is about network decomposition. Okay. Can be, this problem appears in many disciplines, in chemistry, in social network modeling, in biological network modeling. Let me talk about the biological network analysis here. We have global network, basically interaction between other biological molecules, say genes. Okay. The part of network, a subgraph, different subgraphs will become active under a particular condition. Say cancer. We have actually 18 types of breast cancers. They all belong to breast cancer, but each one is different. Some part of the graph will be active under a particular condition. Some will not. Now the task is this. I give you a collection of these networks, not the building blocks. Can you identify those building blocks automatically? And then you can use that to reconstruct original network. The biological consequence is this. I can use that to identify particular potential pathway specific to particular cancers. All biological pathway that's common across several types of cancers. Because they are cancers, they have common features. So that's the biological implication. Okay. This problem looks like a graph problem, but you can summarize this into matrix and then use matrix factorization to address this problem. During this talk, actually, I will focus on the first two tasks. We will not have time to talk a lot about biological network analysis. So I show you a few examples where we can use the matrix factorization. You can also use it in computer vision, in IR, information retrieval in other applications. Okay. So now we have quite a few challenges. How do we handle noise in the data? Okay. How do we model uncertainty? So the answer is we'll use Bayesian framework to do that. We model a generative probabilistic model to model uncertainty and the noise in data. How do you learn dimensionality of Z and A? Relate to your question, basically, what's K? How do you choose K? Okay. Third question is that's really important. Like in face recognition, people use eigenface approach. They use different eigenvectors, use the projection coefficient to do face classification. But once you change the number of bases, you have different performance. You have similar problem here as well. Another challenge is using non-negative constraint. Why do we need this constraint? Why bother? Okay, that's actually rooted in that's motivated by computer vision problem. In year 2000 or 2001, there's a seminal paper called non-negative matrix factorization. They use it for computer vision. Basically, they decompose the image, the face image, into parts. Say, a face can be interpreted by additive combination of parts. Nose, eyes, mouth, put them together, you have a face. If you use NMF, non-negative matrix factorization, you get it. But if you use, say, PCA, you don't. Why? Because in PCA or other analysis, the basis can be negative. Once negative, they cancel out each other. You don't have the nice interpretation, the part interpretation. It cannot be additive in the positive sense. And also, it's very meaningful for many biological problems because you don't have negative gene expression. So it's on or off. There is no negative gene expression. So for many applications, these constraints are desired. We'll show actually this will make a difference in terms of text modeling as well as collaborative filtering. Suppose we have a nice model that can model the noise in the data, can allow us to learn dimensionality of ZA, can impose a non-activity constraint. Then we have a very beautiful model. Then life seems very nice, very easy now. But it's not, because we are computer scientists. We have to solve another problem, which is inference. If I'm a pure statistical researcher, I will just run Monte Carlo. I would be happier. But in practice, if you have millions of documents, Gibbs sampler will be really slow, or Monte Carlo, very slow to give you an exact posterior distribution. Actually, the exact is not really exact because you even don't know when it will converge. Judging the convergence of Monte Carlo method is very challenging. So what we do is, can we develop efficient approximate inference method for these models that I can use in practice? Okay, so this can be shown is normally it's an NP-hard problem. So what the task is develop polynomial time approximation techniques to give you an accurate solution, approximate solution. Okay, Bayesian models. We say we want to model uncertainty in data. Okay, let me address the pointer here. So in a Bayesian approach, we try to compute the posterior distribution of the latent variables. So Z and A. Z is the loading matrix, A is the basis, and the X is what we observed. And that's proportional to the joint distribution of XZA. This can be factorized into the product of prior distribution on A and Z and a hyperprior distribution on Z. This is the likelihood function, X given ZA. So if you look at this equation, really we use a Gaussian likelihood function. So each element of X will follow a Gaussian distribution. And this distribution, the mean of this Gaussian distribution is this, is xi, simply zik multiplied ak, plus the variance will be from the Gaussian noise. Now the issue is how do we design prior distribution? So we want prior distribution to impose non-negativity constraint. So when A has a negative value, we'll give a 0 probability for it. We only allow it to have a non-zero probability when it's larger or equal to 0. And also we want a prior distribution on that such that we can model the uncertainty. Actually, we will penalize a larger model, meaning the model will prefer a small model, meaning K will be small.
Are you summing over? Or?
We'll see that right away, actually. I will talk about the pi. And let's first talk about prior on A, then I'll answer your question about the pi, okay? So I said we want a non-negative constraint on A. So to do that, we use a truncated Gaussian distribution on A. So that says for each element is a Gaussian distribution with a 0 mean sigma A squared as a variance. But I multiply that by a step function. So now this is like a classical L2 regularization, but with a non-negativity twist. So this Gaussian prior distribution is equivalent to L2 regularization, okay? And this will force the distribution to have non-zero probability, only if AKJ is larger or equal to 0. So serve two purposes here. Z and prior on Z. Okay, this is a little bit too abstract. But let's look at a general matrix. This is a binary matrix, okay? And we can have, let's forget this part first. we assign a binomial distribution, Bernoulli distribution on Z. That's the formula. Basically, either this case, either 1 or 0. We assign a conjugate prior on Z, which is the beta distribution. So beta is a continuous variable. Pi Z is discrete. Okay. Now the issue is how do we determine K? How many columns we will have? So one trick is we do not determine it up front. Instead, we set it to be infinity. So now the matrix become a matrix of infinite size.
And these Z's are discrete. 0 or 1?
Yeah, 0, 1. I'll answer that. It's a very nice question, actually. We'll talk about it a little bit later on. There are advantages, disadvantages to making them to be discrete. Anyway, the point actually here is the first point is about determining the K. So we make it to be infinite. Now if we marginalize over pi, in other words, integrate over pi, we obtain a new nonparametric distribution based on Indian buffet process. This is actually developed in year 2005 by Thomas Griffiths and Zubin Garamani. This is a nonparametric Bayesian prior in the sense the model can become bigger and bigger when you have more and more data points. In other words, the K is not predefined. You can change the K, become bigger, not K, sorry. The K actually is infinite, but the effective basis, the number effective basis, in other words, only finite number of columns of Z will have non-zero columns. And this number is finite because normally you don't need an infinite matrix to explain a finite number. So even the matrix has an infinite number of columns, many of them will be all zeros. Only finite number of them are non-zeros. Now the issue is we call it K plus. So we define a method that we also learn K plus automatically from data.
Can you explain why IBP is the best model for this scenario as opposed to Chinese restaurant or any other of the probabilistic models?
Okay, any other. Okay, let me first separate two cases. One nonparametric and one parametric. For nonparametric, you can have variety models. For this scenario, I don't know which scenario you're referring to. You are talking about text modeling, or you're talking about collaborative filtering, or talking about...
I'm saying there's any number of functional forms that you could parameterize the Z given pi distribution.
Uh-huh.
I mean, you're choosing...
I can tell you first up front.
So.
Yes, you can think about CRP. And this is different from Chinese restaurant processes. In a sense, it's more flat, it's more natural as a prior distribution on matrices. Yes, you can use CRP. What CRP does is essentially is a process that will give you a Dirichlet process prior on grouping. How many classes you will have instead of how many columns. Because there you can think about if you ignore all the columns, only one columns, you have a distribution of partitions. You have a finite number of articles. You want to group them into groups. You can use CRP, group them together. But that does not tell you what will be latent matrices to combine different topics. It's a different type of priors. Does that make sense? It's not natural to apply on matrix factorization model.
I'm just curious why IBP is the best parametric form that you're for some of the domains that you chose, or just I mean for any specific.
No, I don't know. I'm not claiming this is the best prior on collaborative filtering. No, I'm not claiming.
Why it's reasonable at least.
No, it's reasonable. I can show you later, but I cannot claim that that's best. No. This word main contribution I can tell you right now is upfront is this. We have this nice nonparametric prior distribution, and we like a good inference method. So we develop good inference, a very efficient inference method. Plus we turn into non-negative matrix factorization. That's the main contribution. We're now trying to do a thorough system comparison in terms of collaborative filtering. No, I'm not doing that. So to do that, we need to compare with all the other alternative methods before I can claim that's really the best. Does that make sense? So to your question,
if I have a problem, how would I know whether this is a good fit for the distribution that I would typically have on the latent vectors in the given domain that I have, whether it's text or...
No, depending on application, right?
For this model.
What type of problem is suitable for this problem? What's the exact question? Can you
if I'm doing a problem in vision or in search or in fit recommending or something, there are certain assumptions that you get out of this, for example, about the way that your topic, the marginal topic distribution will be like, right? You're making choosing a model corresponds to some assumption about the marginal for the topic distribution you'll typically have for your data.
Yes, that's right.
And I guess what I'm curious is that how can I look at the data set and then what would tell me what is the appropriate latent topic distribution for that given domain?
Latent topic distribution for the latent domain. Sorry, I'm not ready for your question. To be honest, I can tell you, for any problem, you have to examine your assumption. Does that follow, this probabilistic model capture the essential aspect of the problem? Okay. But if you ask me up front, even before you see the data, does this model make sense? I don't think anyone can really answer that. It's really problem dependent. You have to look at the data, even visualize that makes sense. Then you can talk about assumptions. If you ask me what model before I see the problem, I cannot tell you. This is a tricky problem, I would say. Really, it's about how do you design a model in the first place, right?
A related question is, so here the Indian process fell out of your choice of pi, right?
Mm-hmm.
The way that you set up the probabilities results in the Indian buffet process when you set k to infinity. Take k to infinity. So can you set it to some different form so that a different prior falls out? Like
it is possible, yes.
Okay,
but not CRP, but it's possible.
Okay, sure, right.
But actually, people have been using Chinese restaurant processes for collaborative filtering as well. Actually, even fancier model, they try to model different groups between users. It's actually the more advanced model, just purely in terms of application point of view. For your question regarding the particular setup of prior that gave us the IBP, it's possible to modify this. You end up with different prior distribution. The beauty of this is actually is the credit to Griffith and Gramani is they actually analyze this distribution, have a nice property by having this setup. We have a nice property on this infinite matrices. For example, they will penalize sparsity. They will have a very interesting description of generating process called Indian buffet process. Basically, how do you generate this matrix can be followed by very interesting metaphor. It's like a CRP. Went to different restaurants, and now they have different dishes from a buffet. So that's the elegant part of this prior distribution. From practical point of view, actually, you can don't use it at all. Don't use this nonparametric matrix formulation at all. You can start finite model, do model selection, like a classical probabilistic PCA. That is fine as well. I'm not against that. I'm just saying we provide you a new inference method for nonparametric Bayesian techniques. But if you really want to do parametric, say PCA or NMF, which is possible, you don't take k to infinity. You can still work out all the formulas. That will be another story, essentially. You're going to compare all the alternatives, seeing which one is really best for which application. Okay. So this is okay, let's skip this for the time being. This actually follows the metaphor we're talking about how do you generate this IBP process. Okay, I can give a little bit of description. Okay, let's skip it. This is quite abstract. It's not the essential about this talk. Now the task is inference. Once inference, the task is to compute the posterior distribution of the model. Okay? But since Z has an infinite number of columns, if you directly compute the posterior distribution, not this one, but Z directly, you have a huge model, okay, first of all. Second, if you want to use variational inference, for example, assume some of you are familiar with variational inference, you have a weird situation because this distribution, Pz, when k goes infinite, pk becomes, the probability on Pz becomes 0. So when you apply variational inference, the lower bound of the cost function becomes 0, actually negative infinity if you take log. So it's yield defined. You cannot apply lower bounding technique to derive a variational inference method for this model. So to address that problem, we define equivalent classes on IBP matrices. So what do we mean by equivalent classes? That said, we can have an infinite number of columns, okay? But many of them will be all zeros. What really matters are those columns that has a non-zero elements. And many of them, if we have infinite number of them, will be identical. Okay? So what we do is collapse those. If we throw out all zero columns, if we only look at the non-zero columns, and we can obtain identical matrix from many different infinite matrices. So we define this as the equivalent class. We use this to represent the equivalent class of that, because they contribute identical information to the likelihood. So this is basically the likelihood principle. When you change the priority, you don't want to change the likelihood function because they provide you this function. It's identical. It does not change this likelihood function at all. So if we do that, the good news is now we can derive a meaningful variational inference method for the posterior distribution on A and the pi, as well as the equivalent classes of that. So to do that, we use variational inference, as we mentioned before. We factorize the joint approximate distribution into this particular form. And in other words, we factorize them into smaller factors, assuming they're independent. So the functional form is simpler than the original posterior distribution. Then we minimize the KL divergence. You can think about the distance metric between two distributions. Then we minimize that over the function of qzik, q pi k, and qaj. If we do that, we have a nice message passing method. Essentially, each time we update one approximation factor, and iteratively we'll obtain, in the end of the day, we'll obtain the true posterior, the approximate posterior distribution.
So how do you set k here in your variational distribution?
Yes, so that's the question I'm going to answer after this. But very nice question, very good. From lower bound, we can approximate the evidence. Actually, not k, the k plus. Then we basically pick the k plus that will give you the highest evidence. When I say evidence, I meaning the marginal likelihood model we marginalize over z of a and pi. So it's basically pk plus given data. Okay? So it's sequentially we have starting in the method work like this. We have two bases. We add one, and then we examine the evidence until it decreases. Then we stop. So the funny part is, even though it's a nonparametric model, we're using model selection. We are really using marginal likelihood to tune k plus. Okay. Now there's another issue. It's about the PA. If A is a Gaussian distribution, actually we don't have this message because we can easily have it. If we approximate A distribution only as a Gaussian distribution, Gaussian prior will be easily incorporated into the posterior distribution. But if A has a truncated Gaussian distribution, the inference is much harder. Variational inference does not apply. It cannot apply it directly with the truncated Gaussian distribution. So now what do? So the trick we use is a power EP method. In other words, we use two types of inference method in a unified framework, which is a power expectation propagation. So we use variational inference to compute the messages on pi k, the message from data to the column of basis, and to the loading matrix Z. We use expectation propagation to compute the approximation, the message to the latent basis, the column latent basis. And this involves minimizing two types of KL divergence. One is the KL from Q to P. Q is approximate distribution. P is exact posterior distribution. One is the minimization of KL P to Q, where again P is exact, Q is approximate. The power EP framework essentially is built upon alpha divergence. these two distributions actually are special cases of alpha divergence. By choosing different value of alpha, you end up with different types of K divergences. So therefore, by minimizing a consistent, essentially while varying the value of alpha in this framework, in this optimization framework, to end up with these minimization updates. I'll skip that, now talk about result. Here's the image decomposition problem. Very simple. I will demonstrate how it works. We have 4 images, okay? If we put them together, we can generate some combinations. For example, if we combine this and this together, have this image, but without noise. Then we can add a noise to it. Then I didn't plot it, you have an observation, noisy observation. So you can combine 2 bases, have this 3 bases, have this one, plus the noise, you have another observation. Now give you the observation, can you infer these latent images? And here is the result. Actually, I didn't plot it. All this method, all the inference method, because this is a really simple problem, will recover original basis, but up to some noise. But let's compare them, the accuracy. So this is time, this is accuracy. Okay, this is a toy example. You can see with Gibbs sampling, if you have lots of samples, with more and more time, it will give you fairly good estimation accuracy. This is error, the smaller the better. If you use a particle filter, sequential Monte Carlo techniques, you have this curve. This is also proposed by Griff's group later on, after the first paper on IBP. It's faster. If we use more samples, it will converge to here as well. But the interesting part is this. If you use variational inference, you can see the converge right away. If we use bad notation, power EP infinite non-negative matrix factorization, referring to the technique we developed, we are faster, but also have even better estimation accuracy. Why is that? Because this uses deterministic approximation, but also uses non-negative constraints. So it's not only about inference, but also we change the model. For these 3 models, the power distribution on A is Gaussian. We regularize the elements of A, but we do not force them to be positive. Here we force them to be non-negative. Then it's even better. Here is the result on collaborative filtering. In other words, the rating systems. We have just a data set. The data set contains 100 jokes and 73,000 users, about 73,000 users. We basically have 10 subsets. We average the results. Each time we hold out 10 ratings for testing. X-axis is the number of bases. In other words, K, or K plus. Okay, this is the accuracy. The smaller the value, the better. We have 4. We'll compare 4 methods. The red curve is the classical non-negative matrix factorization. So in this model, the Z actually is continuous. It can be from 0 to infinite. Blue curve is from SVD, so it's very similar to PCA. But the red dot, actually it's not red rectangle, is the result from infinite NMF. Is our new method. Use power EP plus truncated Gaussian power. The blue dot is a classical IBP model, but with variational inference. Using this model, we learn the number of bases automatically. Basically, we increase the evidence. And that's the result from the other 2 methods. Here we just plot by varying number of bases for all the other methods because we do not, they are not in a Bayesian framework, so we are not using probability to tune the number of bases automatically for them. So we just plot all of them across a wide range.
So for the infinite matrix factorization, there is some element can be inactive, right? I mean, for the IMF.
For IMF, yes, some elements of A can be negative.
Okay.
Yes. Actually, this shows using this non-negativity constraint, it helps.
Yeah, right.
We get better results. This is on topic on document modeling. We use this is a very popular data set, 20 news group data set. Okay, have 7,500 articles, lots of words. If we apply IMF, we end up 6 topics. Oh, a typo, okay. 6, now 16. 6 typos from IMF. In other words, the classical matrix factorization, but with IBP prior. If we use this new model, end up 16 topics. Actually, in our paper, which is under review, we also apply LDA and classical NMF models on the same data set. We compare them. But they basically obtain very similar result in terms of compared to INMF. If you look at these 2 models, this is really comparing 2 models to show you the benefit of having non-negativity constraint. So first of all, you have fewer number of bases for IMF. If you look at the words inside each topic, they're more diverse. For example, game, cars, windows, DOS. They're not really, shouldn't be together, okay? If you look at this one, topic on Windows, DOS, MS, network, program.com, they're very consistent about computer. This article has a computer topic. If you look at topic 2, the God, Jesus, Christian belief, yeah, it's very consistent in terms of finding latent topics. This one is space, question, light, NASA, science, Earth. It's about science. So, this I want to talk about a little bit comparison with the LDA, even though I didn't show you the result from the popular topic model. LDA stands for latent Dirichlet allocation model, which is basically a hierarchical Bayesian model. You have a Dirichlet distribution at the prior distribution for the mixture component. You have a multinomial distribution for each mixture component. Okay. The difference is this: that LDA is a mixture model. One document can have 5 topics, but this document can either belong this topic or the other topic. The assignment will be probabilistic. You can have 0.9 chance belong one topic, 0.1 chance belong another topic. In this matrix factorization model, a document can have 2 latent topics simultaneously, because Z is binary. Okay, I can have very high confidence on 2 elements of Z, making them to be around 1. In other words, I have one document will be very likely simultaneously belong to 2 topics. So that's the difference between the actually mixture model and this matrix factorization model. Okay, any question?
What do you mean by simultaneously belongs to 2 topics?
Oh, simultaneously. This. Okay. Xi equals 1, 0, 0, 1, 0, for example. This is topic 1, let's use T1. Okay. That's A1, A2 to AK. This can be 1, this can be 1. Each row of A corresponding to one topic. I can have 2 non-zero elements simultaneously.
Okay, so if I want to do clustering based on the factorized result,
you can use this matrix. For example, this document 1, document 2, you have 0, 0, 0, 0, 1. Okay, another document X4 is 3 is 0, 0, 0, 1, 0. Now I'll say these 2 in one cluster because they have identical loading matrix, right? They both have 2 topics. Does it make sense? Okay. Actually, I want to emphasize, really we have posterior distribution on all the elements. Really, it's 0.1, 0.9 on each element. This is the deterministic, is a sample from the true posterior. But really, we have a posterior distribution on all the elements. So in other words, we say how likely you belong to the topic 1, how likely you can belong to topic 3, 4. But each one can have very high confidence at the same time. This makes sense in some scenarios. But for some application, might not. It really depends. This is the result on network decomposition. We compare with in terms of reconstruction error. We compare with the Monte Carlo methods. proposed by Griff and Rubin Garamani. So this is the error plot, scatter plot. So the lower the better. So in the new method, deterministic approximation gives smaller error. And we change the network overlapping, we change the noise, we examine different patterns basically. How many bases we have, for example, and how many noise we have. We examine consistently the new method better than using Monte Carlo method. But I have to emphasize this. This is using finite number of computation. If I run Monte Carlo forever, there will be Monte Carlo actually would be better. But for the IMF, not for INMF. For INMF, because of the new constraint, we can still have a chance of getting better reconstruction error. So I have a simple conclusion. Basically, we have concept model plus Bayesian framework. And so that's essentially the truncated Gaussian prior with IBP prior. We develop a new inference method. This could be used, potentially used for many applications. And I have to say, I haven't tested thoroughly on any of them. But this is the beginning. Okay. So any question? Hope I haven't confused all of you.
About network decomposition. You also compare with spread clustering. And the spread clustering is also kind of a matrix factorization.
Which method?
Spectral clustering.
Spectral clustering, yes.
It's also kind of
but you have, yes. Yes, it's different, right? First I have to compare how many clusters you're going to use, how many groups, right?
Okay, so here you need to identify.
No,
Okay.
I don't.
Okay, that's
How about, like, can you compare like the computational time required
For what method?
for like against like, simple SVD decomposition or something like that?
No, we didn't. We didn't compare with SVD. We compared with the Monte Carlo method,
Yeah.
but I didn't compare with SVD.
So just wondering, like, what's the size of the problem here you're
This
talking
image, this image is very small. If it's a large problem, you cannot run Monte Carlo. Like, yeah, this is synthetic image. If it's a large image, I even cannot make the plot for Monte Carlo methods because it's too slow. Yeah.
So do you have the tools we use?
Yeah.
Open source?
No. Well, paper hopefully will publish in a month.
You don't have a tool?
Not yet. But we're happy to establish collaboration. I can give you a. No, I don't have business card with me now. I can write down. If you give me a card, I can write an email to you when it's ready.
So this like, did you write this in MATLAB or something? Or
Yeah. You can have an intern turn it into a GP to some C class. Okay, thank you. I'll send you an email.
Great, thank you very much.
You're welcome.
All right. Thanks.
Okay, so we're done.